Welcome to the second lesson on Fourier series. Today we work with discrete time signal. And don't forget that the Fourier series only exists for periodic signals. So we are working on discrete domain and with periodic signals. So far, until now, we learned a lot about signal system, about LTI systems with the convolution. And in the last lesson, we studied about Fourier series in continuous time domain. And with today's session, we move from continuous time to discrete time. The structure of the lesson will be kept more or less the same with the continuous time domain. So lesson with only 4 simple parts. The last one is there. There's a list of exercises that you should try in the textbook. The objectives, as usual, there's 3 checklists to help you to make sure that you understand the lesson or not. So the main content is about the Fourier representation in discrete domain, and then some properties of Fourier series. And at least you know how we end up with that Fourier transform, our Fourier series, how we can develop that. The first objective is you must be familiar with by the end of today's lesson, discrete signal, complex signal. You should be able to find Fourier coefficients of any discrete periodic signals, and you should understand various properties, many properties of Fourier series in both continuous domain and discrete domain. So this is how we define a periodic signal in discrete domain. So with discrete domain, as long as the signal repeats itself after certain times, then it's called a periodic signal. And the minimum number that satisfies this condition, the minimum must be positive for sure, non-zero, is called the fundamental period. And if you take 2 pi divided by n, we call that the fundamental frequency. So about periodic signal in discrete domain, this is all definition that you should know. Let's take a look at some very basic periodic signal. The cosine of 2 pi n over 10. So that is n. When n equal to 0, you have 0 cos 0. You know that in the circle, the cosine is there. That is the sine. At 0, cosine equal to 1. When n equal to 5, n equal to 5, we have 10 over that pi, and pi equal to minus 1. The cosine of pi is minus 1. So 1, 0, 1, 2, 3, 4, 5. n equal to 5, then we have minus 1. Minus 1. So 1 point there. Oh. 1 point is there. Another point is there. And you know this function is there. So that is the cosine signal in discrete domain. Okay, the real signal. What about a complex exponential signal like that? So e power j omega 0 n. So basically in this case we need a unit circle in the complex plane. Real, imaginary part, and then the unit circle. So with the unit circle, we can totally visualize the signal xn, e power j omega 0 n. So let's pretend that that is omega 0. So 2 times omega 0 going to be there, double the comma. So this point is basically e power j 2 times omega 0. This is e power j omega 0. And if we keep moving on like that, with a bunch of points, like that. So this is how the complex exponential signal look like if you really want to visualize in the complex plane. And actually it really repeats itself after a certain time. So it's a rotate around that circle, moving around, and then moving around. Okay, so that is the basic knowledge of periodic signal in discrete domain. Let's move to the math part. We will try to derive the Fourier series, but for the case of discrete signals. And in order to do that, we need some help. It's like the case of continuous time. We need some integration equal to 0, like that. So we're gonna try to copy the same technique. So first thing, we need to solve this sub problem. So we have the answer here, but so we'll try to prove that. The idea is that we have the periodic complex exponential signal like that, e power j k omega 0 n. So omega 0 is the fundamental frequency given by that 2 pi divided by n. So think of omega 0 as a constant. That's all. The sum is taken within one period. So basically, it means that we can take the sum from 0 until n minus 1, or we can take from 5 until n plus 4. Basically, any period. We can take any period. But for the sake of simplicity, often we take that interval, the sum within that. So we have to prove this, the sum of that, or the sum of that equal to n, the fundamental period, if k equal to 0 or the multiple of n. Otherwise, the sum gonna be equal to 0. So please stop the video for a while and try to prove this property. At least give it 5 or 10 minutes to try. So let's prove that. Consider the easy case first when k equal to let's say n. So in that case, when k equal to n, that exponential become j k. Replace k by n 2 pi n multiply n, and that basically j 2 pi n. So the e power that become e power that. What is this? This is a complex number. And you plot the unit circle. Where to find the angle 2 pi n. Where is 2 pi? Actually, this is 2 pi. So 1 time 0 is there, 2 pi is there, 2 times of 2 pi is still that point, and n times of 2 pi is still that point. So basically it means this one equal to 1. So if we take the sum within one period, it means the sum of n value, we end up with the value n. So first part is done. For other case, and then we gonna do the geometric sum. The sum of e power j k 2 pi over n and on power n. The sum gonna taken from 0 until n minus 1. What is that? This one equal to 1 minus e j k 2 pi n and on everything power n divided by that subject for that parameter. Okay? The geometric sum, you remember? The sum of n equal to 0 until n minus 1 of q power n equal to 1 minus q power capital N divided by 1 minus q. So in this case, with the same reasoning, you can see that this one is 1 minus e power j k 2 pi. Well, with some big number there, j k 2 pi over n. And you see that guy with the same reasoning up here is equal to 1. So that equal to 0. So it confirms second property there. So this sum take only two values, either n or 0, depends on the value of k. So by using this property, we'll be able to derive the Fourier series pair for discrete case. Let's say we have xn is a periodic signal with the period n, and let's say that xn can be decomposed into with the sum of the fundamental exponential complex exponential signal like that. What is the value of k? Ak. To find ak, the hint is calculate the product between that with that, and then we take the sum over n terms. Normally again you can take from 0 until n minus 1, and we apply the properties in the previous slide, and we have some number, some value. So please stop the video and try to find ak. So let's do it. Xn is up there, so I just copy paste from here, replace the sum from 0 until n minus 1. So it's the first sum of k equal to 0 and n minus 1. Put ak e j k omega 0 n, and then multiply that e power minus j r omega 0 n, and then we take the sum over n terms. So we take the sum of n, go from 0 until n minus 1. We combine these two guys because they have a lot in common. The only difference is k and minus r. So we have e power j k minus r omega 0 n. We can take the sum of n here, n equal to 0 until n minus 1. ak could be put out of the sum, and here we have the sum of k. And this one, I hope you find this one very similar from the previous slide. It take the value of n if k equal to r and 0 else. So it basically means the sum here, AK will be gone when K is different from the R. So that equal to AR multiplied with N. So basically AR equal 1 over N multiplied that. So in short, 1 over N, the sum of Xn multiplied E minus J K minus 0 N and run within one period of that. So this pair, finally Xn equal to that of AK and AK equal to that is called the Fourier Series pair for the discrete signals. So this is the what I just explained, that's in really beautiful form. Two similar formula, omega and then 2 pi over n. And all signals are calculated with all sum here are calculated within one period. So Xn is the periodic signal, discrete signal. AK is the Fourier coefficients. And highly pay attention that both Xn and AK they do exist from infinitive until infinitive. And they are both periodic. Be careful attention with that. Let's do some exercise to demonstrate the Fourier coefficient in discrete case. So consider this signal. This is the real discrete signal. Let's try to find and plot Fourier series for this signal. Apply the Euler formula. Remember the Euler? E J phi equal to cosine of phi plus J sine of phi. That's the Euler formula. So in this case, X is equal to e power 2 pi 5 n minus e minus j 2 pi n over 5, sorry, n divided by 2j. So with this example, what is the fundamental period? And following the definition of this slide, compare these two formulas and you see n in this case to 5. And the value of A1 equal to 1 over 2j, and then A2 minus 1 equal to minus 1 over 2j. I emphasize again that AK is periodic, so it means that we do not have only A1 and AI minus 1, but we also have other values. And to visualize it, it should look like this. So A1 equal to that. A minus 1 equal to that. Totally right. But then, because AK is periodic, so we still have A at 4, which is equal to A at minus 1, A at 4, A at 9. And A at 6 equal to A at 1, and then A at 11. So this is the Fourier series coefficients of the signal xn, and that will go to n to infinitive. For the second exercise, we gonna apply the same concept, the same technique. Please stop the video and do this exercise now. Do not take a look at the solution, do not skip the video, do not move forward, just stop and try to do it yourself. Apply the Euler formula, that is the only tool that you need to do this exercise. You are more than capable to do this. Believe that. So I guess majority of you end up with n equal to 5, the fundamental period, and you go to find a3 equal to 1 over 2j, and a minus 3 equal to minus 1 over 2j. But then do not forget that the signal is periodic with the fundamental period equal to that. Then if we visualize how does it look, and here we go. Actually, it's there that I showed you before, but then we have sum at 2 and then minus 2. Because of the periodicity of Fourier series coefficients. Okay, so if you finish with exactly the same shape, I'm really happy that you did correctly. Congratulations. So that is basically everything concerning the definition of Fourier series in discrete domain. It basically says that any periodic signals in discrete domain could be decomposed into a bunch of AK with the sum of AK. We have multiple properties, but then I think that there are only two that are really important: the multiplication and the passive. The multiplication, they basically say that if xn, ak is the Fourier series xn, bk is the Fourier series yn, and then if we take the multiplication of these two signals, we end up with the same signal, another signal which is totally periodic. The question is, what is the corresponding Fourier series of that? And you gotta guess. We say that the multiplication. We just said we said that in the lesson of Fourier series in continuous domain, the multiplication becomes the convolution in Fourier coefficients. So in this case, we end up with more or less very similar. The a here. The only difference is the sum is not from infinity to infinitive. That would be very silly because these two signals, we know that these two bunch of numbers, they are periodic. So it's go to infinity to infinitive. We cannot do that. So actually the sum is taken only within one period. So often we take from 0 until n minus 1. So that is the only difference between this and the convolution. The convolution sum, we take the sum from infinity to infinitive. And that one, people call that the periodic convolution. So it's still a special type of the convolution. So with that case, we still can safely say that the multiplication in time domain becomes the convolution in Fourier domain. The Parseval, still the same thing. With the continuous case, replace the integral by the sum, that's all. And instead from infinity to infinity, wow, it's exactly the same. In the case of continuous, we take the integration within one period. Here we take sum within one period. So the idea here is like the power, and then it could be calculated by simply take the square sum of square upon Fourier coefficients. So that is pretty much everything about discrete series, Fourier series in discrete domain. And here are some homework that I hope you will spend some time to work on them. Okay, good luck.